Hello everyone, welcome back to Math 214, Foundations of Mathematics. Today we're going to talk about the countability of sets. So we had this warm-up problem. If you had time, think about the warm-up problem. Let's quickly talk about them. So is there a bijection between these two sets? Well, the answer is no, because, well, these two sets has different number of elements, right? Remember, a bijection means there's a one-to-one correspondence between the elements from the domain to the codomain. So if there are finite sets, they should have the same number of elements. So the short answer is no. Okay. What about this one? This one where union an extra element 0 into the set natural numbers, right? So this natural numbers, the subset of this set, adjoining 0. But is there a bijection map here? Well, the quick answer is actually yes. And what's the map is we can send any natural number union 0 to n plus 1. So it's okay if you haven't thought about this, but we're going to talk about it later. But what we're trying to see from this warm-up problem is there's a huge difference between finite set and infinite set, which we're going to talk about here. So to summarize, we find the following thing. Well, it is impossible to have a bijection if A is a subset of B and A and B are finite. But it is possible if they're infinite sets. Okay, so this is the observation we have from this warm-up problem. Okay. And this is indeed a very huge difference between finite and infinite sets. Right? If they are finite, this is not possible. If they're infinite, this is indeed possible. Okay. We're gonna see a little bit more of this example from n union 0 to n. So this is in history a very famous problem explaining this kind of phenomenon, and this problem is called Hilbert's Hotel. Okay, so here's the story. The Hilbert's Hotel is a hotel along the street where there are infinitely many rooms. So I could call the first room room 1, second room 2, and so on. Okay, so there are infinitely many rooms. Assuming that this room is already, these rooms are already completely occupied by people, so there is a person called person 1. This person 1 is living inside of this room 1, and there's a person 2. Living inside of this room 2, and then so on and so forth. Okay, so these are rooms, and these are people. All right. So now here's the problem. Today we have one extra people who are trying to live in, and let's call this person an extra person 0. Is there a way to accommodate this person into the rooms? Well, this is not possible if we're in an actual hotel when there are finite many rooms, right? Because all the rooms are occupied, there's no extra room for this person to live in. Well, if we are in this case of Hilbert's Hotel, where we have infinitely many rooms along the street, there's a way to do this. Well, for example, we can move this person 1 to room 2, move this person 2 to room 3, person 3 to room 4, so on and so forth. Alright, so what we will get? think about, we have still all these rooms. Room 1, room 2, room 3, room 4. Well, now room 1 is living in room 2. Everyone is moving to the right for one room. So room 1 is now in, person 1 is now in room 2 now. And this person 2 is now in room 3, and person 3 is in room 4. And surprisingly, we have one extra room coming out, which is room 1. This is now empty, there's nobody living inside of it. And then this person 0 can just happily move in. We have person 0 now. And then you see, we can accommodate one more person, even though our hotel is completely full. This person can move inside without kicking out any of our residents. Okay. So this is a very interesting situation. This is, again, the important thing is we definitely need to have infinite many rooms. Otherwise, someone will have to move out. But this is possible when we have infinite many hotels. Okay, so let's observe this phenomenon again, use mathematics. So what we have actually done is we actually construct such a map. The map is defining by we map the person to the room. So person 0 is now in room 1, person 1 is now in room 2, person 2 is now in room 3, and so forth. So in general, person n will be living in room n plus 1. Okay. And moreover, this map is in fact surjective and injective. So this is the bijective map. I have talked about injective functions, surjective functions, and bijective functions before, right? We can check this as a bijective function. Just to remind you that there are at least two ways for checking a function is bijective, right? So the first way we can do is we can try to show this f is injective and surjective. This is one way. And another way we can do is we can construct the inverse of it. Construct G. Which is from natural numbers to natural numbers union 0. Remember, we have to switch the domain and codomain for the inverse function. And then check that f composed with G is equal to identity, and G composed with F is another identity map. Okay, so these are the two ways that we can check this function is actually bijective. Okay, just to remind you how to construct this function G is that we want to basically want to assume there's some element in the codomain, and we want to check there's an element in the domain. So this is part of the proof of a surjectivity. So that f of m is equal to n, and we want to solve this m out using n. So which is equivalent to m plus 1, where f is sending into plus 1. So m plus 1 is n, which means m is n minus 1. So in this way, we can find this map out, which should send m to or n to n minus 1. Okay. Just a brief reminder that this is something we have practiced a lot. This is how to find the inverse function. It's part of the proof of surjectivity. Okay. Any question? Yeah. Okay. So now let's move to our definition today. we say this A is countable if there is a map, there is a bijection from A to natural numbers. Okay. So in this way, we define what is a countable infinite set, and we say, in general, what is a countable set? We say a set is countable if it is finite or infinite countable set. Okay. So any countable set is either finite or an infinite countable set. I do want to explain this definition for a little bit. Why do we call this a countable set, a countable infinite set? So the set of natural numbers is like the set of counting numbers, right? This is how we count things: 1, 2, 3, 4, 5, so on and so forth. And a bijection between A and the set of natural numbers means, well, the elements in A are exactly like labeled by 1, 2, 3 according to this bijection, right? So this is why a set that has a bijection with the natural numbers is called countable. Okay. All right. So let's rethink about what we did here. Here, what we did is we constructed a map f from n union 0 to n, and I told you that this is a bijection map. We haven't like checked everything yet, but it's not so difficult to check because we have constructed, for example, the inverse function, and we can check these two identities, but practice this kind of thing a lot. And what we just proved is this is a bijection map, which means by definition, this whole set in union 0 is countable, right? Because this is how we define a countable set. There is a bijection from this set to n to natural numbers. So we just proved we need some further check that we need to check that the compositions are identity. Then we have this a union 0 is a countable set. Okay. And I want to add a remark, which is actually going to be our group work problem. So this remark is, well, we can do something similar, that if we remove one element, number 1, from the natural numbers, then this is again is a countable set. And this is our group work problem. Okay, so far we have seen our example that this natural number union 0 is a countable set. The set of natural numbers itself is of course another example of a countable set, because we can choose here A is the natural numbers, right? And we can fix the bijection as the identity. So I think I should also say that this n itself is a countable set. By choosing the bijection as identity itself. Okay, and these examples we have seen so far only differed by the set of natural numbers by one element. Right here we adjoining one extra element 0, and here we're removing one element from the natural numbers. Right? So here's an example that might seem a little more astonishing when you first see that. So this is our example. Okay. So let's think about this set. I'll call this A. So this is the set of all even natural numbers. Right, this contains, see, like n is the natural numbers, so we have like 2, 4, 6, 8, all these elements. Okay. And we're trying to show the claim here is prove that A is countable. Okay. So this is a little bit astonishing when you first see that, because, well, this set itself is a lot smaller than the set of natural numbers, right? Because we're removing all these even natural numbers, which there are infinitely many, we're removing all these odd natural numbers. There are infinitely many odd natural numbers, right? Like 1, 3, 5, 7, all this that goes forever. But this is still countable even after we're removing infinitely many elements. Okay. And we need to come up with a problem, with a proof. Okay. So the proof itself is not very difficult. Because think about what is this set? Is all these elements 2, 4, 6, 8, 10. We want to map it to somehow the set of natural numbers. Right? So what can be a map that is bijective between these two sets? Well, straightforwardly, we can just like map all these elements correspondingly, right? We map 2 to 1, 4 to 2, 6 to 3, so on and so forth. Like this. Okay? And then we can formulate this map and try to prove it is a bijective map. Okay, so what is this map? Well, every time we're dividing by 2, right? So we construct such a map from this A to N. We define it as n over 2, right, for any even natural number. Okay. And then we want to show that it is bijective. Okay. So how to prove it is bijective? Again, we have two ways we can try to show it's injective or surject, and we can construct the inverse map. Again, the inverse map, how do we construct it is by solving this equation out. We want to assume something further according to that surjective proof, but this is how we do that. Okay. So prove this by construct the inverse map. Again, we're going to do that, write down the definition of a surjective function, right? So we want to show it for all n in N, there exists some M in A such that f of M is to N. Right, which is the same as, well, this Fm, according to this definition, is M over 2, which is to N. And we solve M out. That's the key point. We want to solve the element from the domain out. We want to solve M out, which is to N. Okay. So this is suggesting that the inverse function, what is the inverse function? The inverse function should be from N to A defined by G of N is equal to 2N. Okay. And then after we need to check two things, right? F composed with G is identity and G composed with F is identity. check F composed with G is identity. Okay, this is something that we've done a lot of times. That we pick a generic element. Remember, F is from A to N, right? Okay, so we want to pick an element in a generic element in the domain. Okay, so we check this, F composed with G of this N. Well, F of N is N over 2, right? So it's G N over 2, and then G is multiplied by 2. Okay, so this is N over 2 multiplied by 2, which is N. Okay, so this is all right. And then we have another one. We need to check that G composed with F is identity. And then we pick a generic element in the domain of G, and then we check that for this generic element, we calculate G composed with F of this M, which is 2M, Gm is 2M, and composed with F, which is 2M. Okay. So this is a concrete proof of the set A is a composite set, right? What we did is we constructed the map, and we tried to show it's bijective by constructing its inverse. We construct the inverse map, and then we check that F composed with G is identity, G composed with F is identity. Okay, and then write our conclusion. Is bijective. And A is complement. Okay, so this is a full example to show a set is a composite. This is how we prove it. Okay, and during the group work we have a more astonishing example for if you first time seeing it, then we'll see that the set of integers will actually be another composite set. Okay, we actually use this idea in our proof of showing a set of integers is composite. Okay. And that will be what we're going to do next during the group work.